Welcome back to System Software. So today, we finished up our crash course on the tooling you'll be using for this class. So hopefully everybody has been able to get through some of the exercises. One thing I want to point about the VC exercise, this feedback repository, I got a lot of questions about, there being nothing there and getting this somewhat esoteric message about not being able to merge some path or something like that. You should actually see this message, configure specimens have no such refreshed. This is because there's no commits there yet. We haven't given you any feedback yet. So the grading is automated in the sense that the GTA just runs some scripts, but it doesn't run automatically when you submit your work. So you'll have no feedback when you first set this up. So I just changed the instructions to reflect this so that it's clear. Yeah. For the projects, no, you won't submit anything. So so here I tried to lay it out here. So the project submission will only be on the Git server. Homeworks and exams will be done on web courses. So yes, for these programming projects, pushing to Git is the submission.
But that doesn't auto-submit on web courses or anything, right?
No, it goes to the Git server on Eustace 3. And then it's configured so that the TAs and the instructional staff have access to it. And it's Git, so it's all time-stamped. You can only, normally can only access that server through Git. So as soon as the deadline's passed, we clone it all. And we'll know exactly when you submit it, we'll know exactly what you submitted. And and then you'll actually be able to resubmit without going to web courses and uploading stuff. Sure, yeah.
So in this case, the submission is when we push the README, right?
For the VC exercise, let me see. The submission is when you complete, for the VC exercise, it's when you complete this step 5, the one where you add an additional change to the README. So you can see here, this is the grading schema. So the repo exists, it contains a README file, and there are at least 2 log entries. So in order to have 2 log entries, you would have had to have gone through section 5 as well.
Thank you.
So basically you do everything in this document except the optional ones. So these are just other documentation of how to use the Git repo, which you may need to use in other projects, or in this one if you add the wrong file or you accidentally delete your local repo. This will give you some detailed instructions on doing that, deleting files, cloning fresh copies of the repo, and a little, this is just an example of the workflow. So I put all this under optional, so it would be clear that you don't have to actually do this for the submission. Any other questions on? Yeah.
So when do we know when feedback is posted? Would
you won't know. We'll tell you. You can. So we won't grade until after the submission date. We're not going to do any early grading because that kind of defeats the whole purpose of resubmission, because then you can submit without a late penalty. But I can ask the GTA to put an announcement on EdStem when the projects are graded. But I've also, I've given, for this one, there's not much. I've given you all of the instructions that we run in the script to check these things. So for every project except the later projects where we hide test cases, you'll have everything, all the commands you need to check your own project. So for instance, in the Hello project, there's a section here called self-check. You run these steps, and it's exactly what our script runs. It will go through all of the commands that we run in order to check these grading criteria. Yeah. I mean, it's in there. Those instructions are in there, but it's not listed as a self-check. The VC project, if you follow the instructions exactly and you go through all the validation, it will be correct. So if you just follow the directions there, I mean, it's not, the script is very, very simple for this. It's literally just clones it, checks the README file, and checks that there's 2 entries. So all those commands are in this during the validation. But if you follow that exactly, then it should work. Plus the exercises, so the exercises can be turned in late without a penalty, or not late, they can be resubmitted without a penalty. So these are just to make sure you guys can actually use the tooling. That's what the VC exercise is for. Other questions on logistic stuff? Has anyone done the VC project? Okay, that's good. Was it hard? Was it easy? Yeah, easy, right? Just paint by numbers, learn the command line. Okay, let's go over the homework. This is the homework, right? Yeah, next time. All right, so question number 1, do make files use tab characters or space characters for indentation? Who says space? Who says tab? All right, good. You probably found out the hard way if you actually did the Hello project. I think I even put documentation on what you'll see if you get the wrong character. Kind of an artifact of a very old-fashioned tool. Okay, so let's take this rule here. This is what it looks like. You can't see it here, but this is a tab. So which part of this is the target? Hello, right? The target is this. So on the left of the colon here is the beginning of the rule. You're telling make, this is the file I want to generate, the hello executable. Which is the prerequisite? Hello.c, good. So after the colon, optionally you can put a set of files here. And how does make use these files? What does make do with this information, the prerequisites? Okay, let's move on to the C. What is the recipe? Which section is the recipe? GCC, yeah. So this is the recipe. So we can answer B here, or the question I asked about B after we answer 3, I guess. So in the above rule, what happens if you run make twice, assuming that hello.c builds successfully the first time, or hello built successfully? What will happen if you run make twice? What will happen on the second time? Nothing. It'll just say, hey, all targets are up to date. And part of what makes this possible, although you don't need it for this example, is make will look at hello.c and see if it's been updated yet. It'll check the timestamp and see if it's newer than hello.c. Now, even if you don't have a prerequisite here, if you ask it to build hello.c, it's going to build it every time anyway. But yeah, because hello already exists. But when you have incremental builds and you only want part of the code to be rebuilt, make will actually look at these prerequisites, look at their timestamps, and only rebuild them if their timestamps are newer, or the timestamps of the prerequisites are newer than the target. All right, any questions on this homework? So that'll give you, hopefully be able to sort of look at make files if you ever have to build some code by hand yourself. And if you ever use any build system or any dependency systems, these kinds of declarative build specifications are common throughout all programming systems, even if they're not using make. All right, any other questions on build automation, homework, Reezy project, hello project? All right, let's take attendance. Okay, so today we're going to talk more about the file system a little more deeply than we did last time. Last time we just kind of looked at commands for navigating the file system. Today we're going to go into a little bit of some of the aspects of the file system. So this is not an OS course, so we're not going to actually talk about the detailed implementation. But for reading today, I've given you this paper, which is, I think, a really good one. I think anyone who's interested at all in systems or computing or the history of computing should take a look at this. It's kind of a classic paper that describes the design of the Unix system. It had some novel stuff. It had some parts from prior systems. But if you read this, you'll see a lot of familiarity, like the hierarchical file system, multiprocessing. And it's an easy read. It's not like a very hard academic paper. And it'll maybe give you some ahas about how your systems work today. So it's a pretty short read. It's not that bad. And I'll give you lots of insight into how really most operating systems, consumer operating systems today are designed. Okay, but today I want to give you an overview of the file system, because one of my goals in this class is to make sure everybody understands the file system. All too often our systems today obscure the file system, but most consumer devices have a file system of the Unix-like design. Okay, so if you think about where are my files or what are my files, maybe this is what you think of, right? You think of your file browser. Oops. So file browsers are really useful tools, but this is not the file system. This is just a view of the file system, just an image of the file system. In reality, files do a lot more under the hood of the operating system than you can see just in this picture. So this is just a browser application that uses your file system in order to help you navigate the file system. In the operating system world, what files are is really this abstraction. So files just provide a way to group sequences of binary data. Kind of all they are. They're just blobs of data, plus an interface that allows you to work with them. Now, what do I mean by abstraction? What does abstraction mean here in computer science? Maybe you haven't heard this too much, but have you heard the term abstraction in computer science? Has anyone taken data structures or CS1? Did they talk about abstract data types? All right, so everybody should raise their hand. You've heard about abstraction, right? So what is abstraction in computing? Anyone care to venture a guess? And I don't have a good definition, but I like to hear yours. Yeah.
Taking something complex and making a simple user interface to interact with that complexity.
Okay, yeah, so I think something about interfaces, taking away some of the complexity, that can be one of the benefits of it. Any other thoughts about what abstractions are? Yeah.
I might be thinking of something else, but isn't it when you take something the user is looking at and convert it into binaries the computer can read it?
No, that's not abstraction. Maybe that's another kind of abstraction. That's digitization, maybe. I don't know. Yeah.
It's like looking at a higher level instead of having basic blocks. You're abstracted to a higher level.
Okay, yeah. So you sort of remove details and look at you might call it a higher level, but you remove details. Yeah.
It's like putting up names or set of operations or an abstract data type, for example, like a stat, right?
Okay, that's an interesting way. So the function abstraction, which we'll learn about later, is a named set of computations, a named computation. So that's one kind of abstraction. Yeah. Did someone else have their hand up? Yeah.
I was going to say, like in object-oriented programming, like abstraction is like the example of like a CD remote. Like you can turn on the CD, but you don't know how it really works.
Yeah, so this is used in programming so we heard about the function abstraction, now we have the object abstraction or our data types. You can define the interface to something and you don't actually need to know how it's implemented. You can interact through this abstract interface. And so I think we've zeroed in on at least intuitively what abstractions are. And here's some other examples. I gave an example of a key remote. And so what abstractions do is they abstract away or they remove differences or details, leaving what's common between devices or ideas. I don't have a really academic definition of it, but these are some examples of abstractions. So lock and key. So if you have any kind of key and a lock, you don't have to, just like with the TV remote, it doesn't matter how it's implemented. It could be a tumbler lock, it could be a wafer lock. All that you know is that when you insert the key and turn, it unlocks. When you turn the other way, it locks. And you don't have to know any of the details about how that implementation works. And so there's this notion of an interface. So you can abstract away the interface so that you don't have to know how it's implemented, but you can still use this device. And this abstraction of lock and key is also used in computing, where you have a login password or cryptographic keys. And they abstractly work in the same way, where you have some key or key material that will lock and unlock some container or some device. So there's some good physical examples as well. So if you have, say, a steering wheel, the old or the mechanical way to do this is a rack and pinion, if you ever know anything about mechanics. But newer cars may do drive-by-wire, where turning the wheel doesn't actually move any mechanical part. It sends electrical signals, which then turn the wheels. And also like electrical outlets. It's a classic interface. As long as you have the right interface, a 2 or 3 prong socket, then you can access energy generated from anything. So these are examples of abstractions. And the file in the computing world is one of these kinds of abstractions. So a file is not just my audio on my disk. It's actually an abstraction that the operating system gives users of the operating system. It gives a way to work with these blobs of binary data. And so what the file abstraction does is it captures what's common about storage hardware. So what are some kind of storage hardware that you guys are familiar with? Yeah. SSDs, so solid state. Hard drives, so magnetic ones. And so what's different about them is that they use different physical properties to turn on and turn on off bits. But what's common about them is that they all provide a way to read and write binary data on some physical medium. And the file system, or the files in the operating system, provide you this interface. It just provides a way to read and write data to some, in this case, physical medium. But as we'll see, the operating system uses files for a lot more than just storage. You can use it for Ethernet networking. You can use it for communicating with peripherals like your keyboard. And if you've ever done any sort of Unix sysadmin, you may be familiar with this, or device files, where your RAM, your hard drive, these are actually all loaded into the system as files that you can read and write to using the same tools. So what's the benefit of this? How is this abstraction used? Well, anything that is file-like, anything where you need to read bytes of data and write bytes of data, can be treated as a file in the operating system. That's why it's not just restricted to, say, audio files or files on your hard drive. You can also have files that are mapped to, say, an Ethernet or a USB port. So, okay, so reading and writing, what other kind of operations do we do on files in our OS? Yeah. Executing files. Okay. So executing is a kind of reading of a file, actually. So execution is done with a different part of the operating system, the process abstraction, which we'll talk about next time. But part of doing that is reading the file. You also open and close files. You have this as part of the abstraction. Okay. So let's get into what files look like, how we work with files in the Unix world. Okay, so the contents of a file, from the operating system point of view, is just binary data. The operating system does not care what kind of data this is. From the operating system level, when you create a file, when you read a file, and you write a file, it's just a sequence of binary data. So this is a tool called hexdump, which you can use to print out the contents of a file in hexadecimal. So everybody, you're all familiar with hexadecimal, binary. It's all binary data. And this flag here, -C, will also show you the ASCII code for this file. So if you weren't aware, even if you have text files on your machine, they're not encoded using these Latin characters. They're encoded using binary data. Has anyone ever seen the ASCII table before? I've seen the ASCII table. Okay, so not many. So we can actually see this. There's a man page for this on many Unix systems. And so each letter of the alphabet and each piece of punctuation is assigned a number code. And that number code is what's stored on disk. So for instance, if we want to represent the plus sign, we use, I think this is octal, we use binary decimal 43. to represent that plus sign. Because think about it, if everything's being stored as bits, well, there's no bit for plus or minus, there's just off or on. And so just like integers can be represented using, base 2 numbers, well, these are not integers, right? These are just symbols in some alphabet, in some Latin or Western alphabet. And so the way we can represent them on a hard drive or in a file is by giving them some code, giving them some numeric code. Does that kind of make sense? So that's why when I go to look at the contents of this hello.c file, which, by the way, if I show you just the ASCII of it, is just a hello world file. This is what's actually being stored on disk, or at least a representation of it. This is the binary data that's being stored on disk. Does that kind of make sense? Questions about that?
What's the -C for?
-C just, so if I omit that, it's only going to show you the hex. -C will show you we'll convert it into ASCII. So when I use this, say, cat tool, my console, my terminal, is doing this conversion for me. It's representing it with characters. But hexdump will allow us to see what the actual binary data looks like, or a representation of that binary data in hexadecimal notation. Questions on this? This sort of makes sense? So this is the difference between how a symbol is represented, like the symbol H, and what it means. So these are just numeric codes. They have no intrinsic meaning for H. You could pick any code you want for this. The ASCII is just a standard for doing this. Or plus, plus may mean addition, but on disk it's just stored as kind of a conventional number that's selected by the designers of this ASCII code. All right, any questions on this? Yeah.
What are we gonna do with this?
What's the point in learning this?
Yeah, no, I'm not like gonna have it. Like, how are we gonna use it? How
Well, okay, so this, you mean the ASCII code or just files?
well,
Well, so for the ASCII code, when we get to compilers and we see how to take a language that's written in ASCII, which is just kind of this arbitrary code for numbering glyphs, for numbering symbols, that has no intrinsic meaning. So we, as the creators of the compiler, need to impart that meaning by translating it. So that's why that matters. When it comes to the file, I just want to show you that this ASCII code, this name, this extension, this has nothing to do with the actual contents of the file. The actual contents of the file is just binary data. It's really the difference, it's really like a map territory problem. So we have the thing itself, which is just the binary data, and then we have our interpretation of it. So this hello.c is not part of this binary data in any way. The .c is not part of the binary data in any way. So it's this distinction between the metadata, the stuff that's describing the data, and the data itself. So I think that's a key thing to understand, not just computing, sort of in life, sort of philosophically to understand. And then I'll show you some interesting tricks with this and some security implications of this. And then when we get to compilers, we'll see how we actually have to impart meaning to these symbols. That hopefully sort of answer?
yeah.
Okay, yeah.
Why are the values different between them? Because like in hexdump -c, in the first it's 23, then 69, but in the second one it's 69.3.
Does anybody know why this might be? I think it's little endian versus big endian. Did you guys have to learn about this in like architecture? They didn't teach about little endian, big endian. It's just how it's represented. I think it's just how it's represented in the file. I think. I might be wrong though. It's just the order. It's whether you store the lowest significant bit first or the highest significant bit first. I think that's the difference, but I'm not sure. If anybody can correct me, I'm pretty sure that's what's going on here. So these are like the individual bytes, I guess, stored out, and this is how they're stored as a single like x86 word, I guess, or half word or whatever it is. I'm not an architecture person, but I think it's little endian versus big endian. But yeah, good observation. Maybe they say that in here. They don't. Yeah, I think that's the reason. Okay. Yeah.
So you were talking about, you said you were going to talk about the security implications.
Yeah.
I was just wondering, so a lot of things that people do now is build data mine.
It depends on what's being data mined. I'm not sure. Let's come back to that. Let's see. Let me show you the examples of security implications, then you can tell me if there's something relevant there. Okay, so Hexdump is a tool where we can look at the actual binary data that's backing a file. And so what I want to get across here is that this hex code, this is the file. This contents of the file. This is the file. This is what can be read and written. The file name is not the file. It's like a phone book. You know, you look up somebody's name, it points to a phone number, but that phone number is not a person, right? It's a mapping between that name and the phone number. So it's the same thing here. This file name has little to do with the actual contents of the file, or at least there's no mechanical connection between them that the system enforces. So this is the concept of the map is not the territory. Has everybody heard this phrase before? Not many people. The map is not the territory. Basically, if you have a map and you redraw a mountain, that mountain is not going to change in the real world, right? So the map is just a representation of the world. If you rip the map, you're not going to cause an earthquake. So same thing here, where if I have, say, an audio file, or say I have this audio file. So I've got this audio file here, this MP3 file, and let me just dump the top of it. So it's just a bunch of binary data, even the ASCII version of it. There's some maybe contents in here, but these dots are non-ASCII characters. So it's just some binary data. I have this tool which will actually look at the binary data and tell me what kind of file it is. So it'll tell me this is an audio file. It'll tell me this is a C source file. And so even if I rename hello.c to an MP3 file, if I rename hello.c to an MP3 file like I've done here, so now I have this hello.mp3, what is the contents of this hello.mp3 going to look like? Is it going to be an audio file? No, it's going to be the same file, right? So it's still going to be this C code. So the meaning of this file has nothing to do with the binary data that's being stored on disk. The file system just helps you read and write this binary data. Yeah?
But if it's so you're renaming only what you're calling it?
Exactly, yeah. Yeah, it's like if you change your name in the phone book, you may have the same phone number.
So if you try to access hello.c, that's just accessing a name that doesn't exist?
Yeah, no, I've moved it, so hello.c doesn't exist. I mean, I could leave it there. I could have both, hello.c and hello.mp3. They're both going to have the exact same contents. So this is why when we talked about extensions, the extension is just an application thing. So at least in the Unix world, the Unix file systems, the extension and the file name has no mechanical influence on the actual binary data. The binary data is the same. The name is just a reference to that binary data. Yeah?
Even when you compile it though, would it still work? Even if it has a .mp3?
Well, the GCC compiler will probably complain because it doesn't like that extension. But yeah, you can absolutely just compile it if you wanted. I might be able to force that to happen like this. Let's see if it allows me to do it. No, it doesn't like me doing that. Yeah. So it won't like the extension. Yeah, it doesn't like the extension. But you can absolutely just compile it. You can compile it. I mean, I can move it to a hello.c file and compile it. Right, because the contents have not changed. You've just changed the name. Yeah.
The contents and the normal MP3 file, what the hell?
Yeah.
Does that hold information about the audio itself, or is that just information about things like author and stuff like that?
So yeah, information like author, MP3 file, I mean, this is getting into like the weeds on other formats that don't matter, but yeah, those MP3 files will store information, metadata in the file itself. So when we see this file type, it says audio file with ID3 version blah, 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 blah. This is just a format within the binary data that will put author, musician information, music information.
So then where would the actual audio go? Because now
Oh, it's in there. It's in there. I just only looked at part of it. So it's all this binary data here that is representing the music file. And so just like with this notion of abstraction and interfaces, this binary data doesn't have any meaning unless you have some tool to interpret it. So just like with our programming languages, when it's ASCII code, there's nothing intrinsic about an ASCII plus sign that means addition. It's our interpreter that will give that meaning. Same thing with the audio. This is just binary, a blob of binary data. If you try to run it as a movie file, it probably won't work. You need some algorithm that's going to interpret it as an audio file. But yeah, this is just a very long, I just didn't print out the whole thing. I used head to just show the beginning of it. Okay, so my main point here is just to show you that the file name is not connected to the meaning of the data. The file system just allows you to read and write binary data, and you can give it a name as metadata. You can reference that file data using a name. All right, questions on that? So there's all sorts of types of files, but these have nothing to do with the name. The file system does not care what these are. It's up to some application that you write to interpret that data. So audio files get interpreted by audio programs, program files get interpreted by programming language tools, and so on. All right, so this file, which I guess I got ahead of myself a little bit here. If you look inside this, look inside this audio file, what some format developers have done to try to include meaningful information in the data is to put the first 3 bytes as the so-called magic bytes. Has anyone heard of this, magic bytes, in the file? Yeah, you've heard of this. What are magic bytes? Yeah, they're metadata stored in the file itself. So this ID3 magic bytes is linked with this audio file ID3 version 2. So this is one thing that the file command looks at. So the file command will actually look at the contents of the file to try to determine what kind of file it is. Now, has anyone ever heard of steganography before? It's a security tool where you hide messages in non-messages, like in images. So even if you have this audio file, someone could use this file as something else. You could hide a written message in here, for instance. So this is still just a form of metadata, but it's stored within the binary data itself. All right, anyway, so that's a little bit of a side. And I think we can skip all this. So same thing, so same thing when you compile this program. So here I've created this hello binary. What do you think the contents of this hello binary will look like? Is it going to look like printf, int main? Is it going to look like C source code? No, it's no more C source code, right? So what the compiler did is it took the C source code and it generated machine code. It generated instructions for our processor. And you can see here the magic bytes here are ELF, ELF. This is the executable format in many, many Unix systems. And our file command will also tell us what kind of file this is. Okay, any questions on this? Yeah.
So magic bytes are like the file signatures, or
Kind of. Well, it's a file type. It's like a sort of a voluntary admission of what the file type is supposed to be in the file itself. So it doesn't rely on the name anymore to do that. So extensions are for applications to look at just the name and try to figure out what kind of file it is. Many formats will use these magic bytes in order to, for binary file readers to actually see what kind of type it's supposed to be. All right, so this has some relevance to security and so this is like a kind of just a basic thing, I think a basic computer literacy thing to understand, that file names are not the files themselves. Just like, our names are not ourselves, right? They may refer to us, but lots of people have similar names, lots of people have different names. It doesn't actually change who we physically are. And so this gap between the name and the thing it represents has actually been used for exploiting people. So there's a technique called masquerading, where you just lie about your file type. And it's been implicated in a lot of sort of high-profile attacks. So has anyone ever heard of the I love you computer worm? This is one of did you learn about this in security? Does you guys teach us? Okay. So this is one of the earliest and one of the largest worms, computer worms. It's probably like in the 90s, I think. It was a long time ago. But the way it worked was really simple. Somebody put a program, a VB script program, visual basic script program, but they put a program, they send it to people in email, and you should know, don't just like execute programs that somebody sends you an email, but they just they named it .txt.vbs. VBS is the name of the program, and by default, I think Microsoft and Apple still do this, but by default, the extension is hidden from you. So when users saw this, they were like, oh, it's a .txt file, it's text, it's no problem. And this person said it was a letter, and it's a love letter, so I really want to look at that, I guess. And they would double click on it, and like millions of people like double clicked on this. Maybe not millions, but enough people double clicked on it. Yeah, probably millions actually. Double clicked on it, and it ran a program on their machine. So you basically just let some random person run code on your machine, and what it did is it just resent itself to everyone in their contact list or something like that. And so while this actually had the faithful extension, because of the way extensions were hidden, people would not know that this was a script, and they would just try to open it, and then the application would get run. So that's one example where the extension or the perceived extension of a file does not actually match the contents of it. This technique is also used to help try to obscure other kinds of executables. So this is a more complicated, more modern attack. You can look at this link if you want to look at it. But one step in this attack is to take something that's purportedly a text file and just rename it to an exe so that it can then be used as part of the attack as an executable in the attack. And there's a whole bunch of these kinds of attacks, just exploiting the difference between the name and what the actual file is, what the contents of the file is. So hopefully that's a little relevance to why I'm explaining this to you. Questions on this? Questions on this distinction? So the map is not the territory. The name is just metadata. It's just a map to a file. And what a file really is that blob of binary data. And in the OS world, it's an abstraction that allows you to read and write blobs of binary data on some storage medium. Okay, so understanding that, the question is, how does this get actually implemented under the hood? How do files actually get their name? So if the file itself, the contents of the file, doesn't actually store the name, where is the name? Where does the name get stored? In the Linux world or the Unix world, let's go into the wrong. So in the Unix world, the way this works is that there are special files called directories. So if files are just blobs of data, well, we can make a new kind of file. We can store in that file mappings from names to files. So it's like a phone book. So this is really what the origin of directories are. Directories are basically like phone books for these blobs of data, for the actual files. Files are just streams of binary data, and a directory gives names to those. It's like a pointer. So you can think of names as just a pointer to the file. So pointers are confusing. The pointers are a simple concept, but they're confusing because of the conflation of the pointer with the thing itself. That's where you get mistakes when you're trying to work with pointers. So directories are basically like pointers, where the names are pointers to the actual file. And what the OS does is it gives a unique ID to each blob of data that kind of persists with that file through its whole lifetime. These are called inode numbers. And then the directories are mappings from names to those inode numbers. So if you're interested in how this actually works under the hood, how it was actually built and designed, take an OS class, because they should go into how file systems are actually built. But here we're just going to look at the kind of user point of view. So one question is why bother? Oh yeah, go ahead.
I was gonna ask, I was doing reading and I saw that it's stored in a table of sorts. Is this table the same as the tree that we access when we do that?
That's a good question. So it's related. It's related. You mean the file tree? It's closely related, and we'll get to that. Yeah, it is very related to the tree. Okay, so why bother doing this? Why not just store the names in the data? Why bother? Why bother having this directory instead of just like making files have the name in it? Why design it this way? Why not make a phone system where whenever a new phone number is issued, it's just like you just dial the person's name or something like that? Yeah.
What if their name is the same thing?
Okay, yeah, what if you have name clashes? So If you have multiple files with the same name, maybe you want to store multiple files with the same name. Maybe you can put them in separate directories. That's any other thoughts on why you might want to design things this way? Yeah.
So that you can rename it?
Renaming is easy, right? You don't have to like open up the file, find it, and edit it. So renaming is easy. Give many files. Oh, you guys should already capture these. And also, if you want to search for a file, you can just look at the directory. You don't have to open up every individual file blob and try to find a file of that name. Okay. So in the Unix world, and you'll see this in the paper that hopefully you'll read tonight, a directory behaves exactly like an ordinary file. So directories are just files. It's just a special file that has a table in it that maps names to actual file numbers, the inode numbers. So it's an ordinary file that, except it can't be written by an unprivileged program, so the system controls the contents of directories. So directories, while they are files, you as the user can't actually modify them. You have to use tools like make dir, remove dir, and move to actually work with them. Okay, so we can actually see this mapping in our command line. So ls is a tool that just reads the current directory file and prints out all of the names. Just by default, it prints out the names. It doesn't print out the inode numbers. But if we use the -i flag, I for inode, this will show us the inode numbers. It'll show the inode number, which is the unique ID of that blob of data that the operating system is managing, and the file. So this is really the mapping from name to inode. And the ls tool is really just a special tool for reading directory files. Does that make sense? Questions on that? I can tell you're completely blown away by this. It's very exciting stuff for you. Okay. So then, move versus rename. How do we rename a file? Like, how would you implement the file rename feature in this system where the names are really just in the directory, they're not in the file itself? So how do you do a rename? What's that? You rename the directory itself? So what if I want to rename hello.c to hello.mp3? What would I do? What's that? Yeah, use MV, but how's MV implemented? Yeah.
Wouldn't it basically just move the inode number to a different end?
Yeah, you just go to this entry here, and you just change this part. You just change hello.mp3. And the number stays the same. Yeah, it's like moving out of your house and getting a new file. I know nobody uses landlines anymore, but it's like having a new person move in. You don't change anything. You don't change anything about the infrastructure of the phone system. You don't change anything about the file. You don't have to edit or delete files. You just go into the directory file and just change the name in that entry. That's it. So that makes renaming really easy. What about moving a file? Yeah, exactly. Name stays the same. You just put it in a different directory table. So if there's two directory tables, one here under here file basics, one under scratch, I just take this entry out of the file basics table and I put it in a different directory.
Are the inode numbers made as it's moving, or is it like slotted that are empty?
The kind of both. So if you move it, it's just editing the directory file. So I didn't go into this. This is more for like an OS class. But whenever you make a new file, the system assigns a unique ID, a new inode number. You can just have a counter, like stored somewhere, like stored on disk. And then whenever a new file is created, you just give it a new number. But the key point is that as long as that file is not deleted, it's still alive, that number will never change. And then all your file operations like move, read, write, they all just work with this directory file, the table. Does it kind of make sense? So it's this sort of virtual thing above the actual file. So there's a long way of saying hello.c is not your file. It's just the name of your file. Yeah.
So an inode number won't change once the file is created. Like it'll always have.
That's right. It'll always have that number.
Like a prison cell number.
It's like okay, yeah, it's like a prison cell number, or like a social security number,
Yeah.
or like a phone number. The phone number. The phone number is not going to change. I mean, you can change your phone number if you're just getting a new SIM card or whatever, right? Or people don't even use SIM cards anymore, do they? You're getting a new like SIM ID. But yeah, you can like change phone numbers to different people. But yeah, So I know, like now it probably seems like a pretty simplistic thing, and I was like wondering why am I talking about like hello.c in the contents? This is why, because this is what you're actually looking at. You're looking at the map of the files. You're not looking at the actual files. The system is managing that for you. And that's why understanding this is important for things like masquerading attacks or efficiency as well, like having efficient algorithms. So you don't need to actually delete this data, copy it to a new file. All you have to do is edit the directory file. All right, good. Questions? Questions on this? So here's a question. Can I put a directory inside of a directory? Yeah, why? Why can I do that? Yeah.
Wouldn't you basically just be saying that in one of those directory ideas, you just basically put another directory table?
Yeah, directories are just files. All files have an inode number, so there's no reason that I can't just add an entry here where this inode number is a file that contains directory information. So here, if I make a new subdirectory called, let me spell it right. If I make a new directory called subdir, and I list out all the inodes, well, subdir, it's a directory, but it's also just a file. It's just a file whose contents has some special format to hold this kind of mapping. So and voila, by just treating directories as files, I've created a hierarchical file system, effectively for free. As long as I have a directory, and a directory is just a table mapping names to inode numbers, and if that directory is just a file, well, now I have a hierarchical file system. Now that seems probably pretty obvious to you now, but this was an invention. This was something that people had to like create and invent. Early MS-DOS, like the Windows lineage of operating systems, did not have subdirectories. It had you had single top-level directories under devices and didn't have this notion of directories as files. So this is the Unix file system design that enabled hierarchical file systems and enabled them to be really efficient as well. Okay, so we kind of went over the hierarchical file system already quite a bit, so I'll just do a quick refresher. But any questions so far on this? So you've learned that the file name has nothing to do with the actual contents of it, and that can lead to security problems. You've learned that directories themselves are just files. They're special kinds of files that have a format that's recognized by make, move, and all those other tools. And you can create a hierarchical file system by just allowing directory files to be inside of the directory table of other directories. All right, so this is hopefully a review. I went over this in the command line, but the root of the file system in the Unix world is called /, and there's only a single file system hierarchy. This is unlike Windows and MS-DOS, where each device or each virtual device can have its own, C:, D:, its own top. It's like a forest of trees. But in the Unix world, there's a single tree. And the way you have devices is you just add them, you map them as a leaf or a node on that tree. All right, let me see what, I want to make sure we have time. Yeah, so in this context, let me show you let me show you again this file system hierarchy. And we'll have a little more context of how it actually works under the hood. So let's take similar example I think we had last time, where we've got our root file system called /. Let's give it a subdirectory called USR. And remember, we had these two special files called dot and dot dot. What was the dot directory? Points to itself, right? It's a reference to itself. So this is how I showed it diagrammatically. And each of these folders has a dot and dot dot directory. So user points to itself. What about user / dot dot? Where did that? It's parent, right? And its parent is root. And I can't remember if I covered this last time, but what does the root's parent folder point to? It points to itself. This is just a convention in the Unix world because there is no parent of the root, so they just have it as a cycle pointing to itself. Okay, so seeing how directories are actually implemented, how can we implement the dot and dot dot directories in our file system. So if we've got, say, let's give inode numbers to these. Let's just say this is inode number 1, 2, and 3. What does the directory table for root look like? How many files does root have here? It has 3 files, right? It has user, dot, and dot, dot. What's the inode number of user? 2, right? What's the inode number of dot? 1, good. And the inode number of dot, dot is 1. So it's very easy to implement these dot and dot, dot folders. They're just alternative names for folders in your file system. And you can achieve this linkage to the parent by just adding a new name into the directory file. Let's look at the user folder. So this is the user folder. How many files are in the user folder? Or I should say directory, yeah, bin, dot, and dot, dot. And so notice, when I say file, bin is also a file because it's a directory. Directories are files. Yeah?
What limits how big the table can get? Because if there is no limit, theoretically, why can you just have an infinitely sized table that just points to one directory repeatedly?
Oh, you mean like have multiple dots?
Yeah, so like, is there something that limits the size so that you can't just say have 1,000,000 dot directories that all point to the same ID?
Well, so one constraint, so 2 things here. One constraint is that you can't have name clashes within a directory. Within a directory, names need to be unique within the directory. But across directories, you can have the same name in different directories. Why? Because they have a different path. So you have a different reference to those. The second one is limits in terms of the size. These are hard limits that are defined by the operating system when you like install or build your system. So there may be like a large, I don't know what the actually, I think we can actually see the limits. Whoops. Oh, no, this is for, oh no, this isn't for the file system. There's some way to view what the actual file system is, but there is a limit to the size of a directory table, and you can configure that if you like rebuild your kernel if you want. But names must be unique within the directory file. Otherwise, it's not a function anymore. You have 2 names or 1 name that points to 2 different files. How are you going to know which is which? How's the system going to know which is which? Okay, so in this table, bin, what's the inode number for bin? 3. What about for dot? 2. And dot, dot? It's 1. So you see that? So in this diagrammatic view, dot is pointing to itself, but all it really is doing is just recording the inode number of the directory file itself. That's where this cycle comes from. And the same thing for dot, dot. It's just recording the inode number of the parent. So even just using this directory tables, we can achieve something that looks like a tree structure, but really it's really just tables. It's kind of like an adjacency matrix that I think you might have learned about in CS1 or CS2. Questions so far on this? Question? That makes sense? So in this scheme where, so what this scheme also allows is I can have, so if I'm in this directory, I have hello.c. If I go into subdir, I can also make a different hello.c. So here I've just made a new file called hello.c. And so now my file system has 2 files named hello.c, right? I've got hello.c in 2 different places. So I can type cat hello.c and I get 2 different files. Why is this possible? Why is it possible to have 2 files of the same name? Yeah.
Because since, for lack of earlier described, since we have 2 different table directories in those different areas, we can have the same name for 2 different IDs.
Yeah. So I have two different directory files, which have their own mappings. So this directory file called file basics is the name that I gave it. It has a mapping from hello.c to this inode number, 435.49344. And if I list the contents of the subdir directory, it also has a mapping from hello.c to some inode number, but it's a different inode number because these are different directory files. Yeah.
Why don't the inode numbers, like, they're all random, it doesn't increment like that.
Yeah, I don't know. The file system is probably implemented to generate them randomly. I don't know. I don't know how this file system generates IDs. It probably has some scheme that doesn't just increment the number. I can also show you the, actually let me just show you the inode numbers again. So notice here we've got this inode number for the subdir. Oh yeah, sorry, go ahead.
Use the clock. The system clock.
Oh, use the clock?
Yeah.
Oh, okay.
Set the clock, all the ideas go back to 0.
Huh. You wonder how, so it must have some scheme. Does it randomize it or something? It's probably random, okay. So here's the inode number for the subdirectory I created. Now notice if I go into this directory and I list out its full directory table, including the dot and dot dot folders, what does the dot folder point to? It points to this inode number. It's the same number, right? So the inode number for subdir in the parent is 444-80965. And the inode number for the dot folder when I'm in subdir is the same number, right? That's how it implements the reference to itself. And same thing if I show you the full table for file basics. So this is the table for file basics. This is the inode number for the dot folder. This is the inode number of the dot dot folder. If I list out the table for subdir, what should the dot dot folder's inode number be? It should be same as the parent's dot folder. This sort of makes sense? I might be losing some people here. Questions on this? So it's the same scenario we saw here where the dot dot folder of user should be root. So it's the inode number is 1. And we see that here where the dot folder of root has inode number 1. The same thing we see here with the dot folder for subdir, the dot dot folder for subdir, and the dot folder for its parent file basics. Yeah.
So you can't have duplicate inodes in a single.
You can't have duplicate inodes for the whole file system. The inodes are unique for all files across the file system.
So like in the root folder, like you could have like both dot and the dot dot, but they both have the same inode.
Yeah, that's right. Yeah. So for the root folder, the dot dot folder is still present to preserve the assumption that all folders have dot and dot dot, but it just points to itself again. It's an alias to the dot folder. All right, questions on this? So this is how you go from just a really simple table mapping names to inode numbers to a hierarchical file system that you can navigate interactively. Parent folders, child folders. So let me show you one other thing. So the file system will also keep track of what are called hard links. Hard links are just entries in some directory table across the file system. So if bin is in one file system or one directory, it has a hard link of 1. So this hello.c file, there's only one link. That is, it only appears in one directory. But for the subdir file, how many directories does subdir appear in? The inode number for subdir. How many directories does it appear in? So here it's in file basics. Does it appear in any other directory file, subdir? Yeah.
It'll appear in the parent itself and any of its children?
That's right, yeah. It'll appear in its parent. So here we see it in file basics. I'll do the inode number. Here we see it in the file basics parent. We also see it in the subdirectory itself because it has a pointer to itself. And so how many links would we expect it to have? 2. Yeah, so we see 2 links here. And same thing with any subdirectory. So file basics itself, if we look at file basics, or look at this directory itself, we see 3 links. We see a pointer to itself and its own directory. Its parent directory is pointing to it, and subdir is pointing to it. So we see 3 links to it. So you can see that here with user, where user is in root's directory, it's in its own directory, and it's in the bin directory, pointing to itself. So I didn't write that here, but it's also pointing to the parent. All right, questions? Questions so far? Hopefully this wasn't too confusing, but you see this a lot in computer science, where you have a simple data structure or a simple scheme creating a complex or rich system out of it. All right, so file systems, so this file abstraction is useful not just for storage systems. It's also useful for any device. This, if you read the Unix paper tonight, it was envisioned as a general purpose abstraction for any kind of I/O. So that's why even today you can go to if you're in a Linux system, you can freely, if you have super user access, you can freely just read and write bytes to your memory sticks. Now, you might not want to do that while your system's running, but you can do that. You can read and write freely to graphics cards if they have a file set up for them. You can hook up temperature sensors. You can hook up USB devices. And you can get a file and use the exact same tools that you use for reading and writing storage files. You can use those for any kind of I/O. And as we'll see in the next couple of lectures, and I think you've seen some of these already, open, read, and write, these exact same system calls, these exact same library calls can be used to read and write any I/O device that has a file hooked up to your system. And we'll see some other fancier stuff like pipes. There's some other special files like random number generator. So if you want to get random numbers in a Unix world, and there's a random number generator file hooked up for you, you just say cat. The same tools you use to print out any other files, you can print out random data. Actually, we probably want to do hex dump because it's binary data. But you can just start getting random data from this special file. There's another special file, /dev/null, which will do nothing with the file. It's like garbage for bits. So if I move something to dev null, it'll just effectively delete it. All right, so I just want to point out that this notion of this design for I/O is not universally used. So there were other schemes for I/O. So graphics cards have other techniques for doing I/O. The internet world was overtaken by TCP, which was the BSD, the Berkeley distribution, the Berkeley sockets. And so you still can use file I/O if you want, but there's a different abstraction for I/O. Anyway, so if you're interested in actually how this stuff is implemented, take an OS class. Files abstraction. File hierarchies are built with directory structures, and you can use paths to refer to files. All right, I think that's it for today. Let me know if you have any questions. Come on up if you have any questions, and I'll see you Thursday.